Okay, good evening. This is Professor David J. De Los Reyes. Okay, my topic for this session will be evaluation of roads. What I will be presenting will be the port road. Then I will give you the summary of the square road and the cube road. Okay? So when you don't have any calculator, you could take the square road, the cube road, and the port road by using this method here. I will show you the secret. Okay, this will be the problem. What will be the port root of 17 equal to? Okay, I will try to bring up the solution. The solution will be actually the the increment in the port root was actually derived from differential calculus. So I will show you how that increment in the port root was derived. We let y equal to x to the 1/4. Okay. Taking the differential, dy will be 1/4 times x raised to 1/4 minus 1 times differential x. We are taking the differential of both sides, right? So this falls under the power formula. It should be n times u raised to n minus 1 times the differential. That u for the meantime is x, okay? So if we try to simplify this one, 1/4 minus 1 is actually 1/4 minus 1. Minus 1 is actually 4/4, right? And 1/4 minus 4/4 is minus 3/4. So to eliminate the negative sign on the numerator, we bring it down. So the increment in the port root of any number will be equal to differential x all over 4 times x raised to the 3/4. These 3/4 here came from this because the difference of this is minus 3/4. We avoid negative exponent, so we put it down. So for any number in which the number is to be taken the port root, the increment in the port root, whether plus or minus, should be dy should be equal to dx over 4 times x raised to the 3/4. This is either plus or minus. Okay? This is not, we cannot just use a computation without having to tell you where that equation came from. And actually, that increment in the port root is actually, or came from the differential calculus. It was derived from differential calculus. Okay? Let's proceed. The number 17, the nearest port root of this one is actually, the nearest number which has a port root is actually 16. So we will place x to be 16 now, because the number is not exactly 16, right? We get x to be 16, and we put differential x equal to plus 1, right? So meaning, the port root of 17 will be the port root of 16, okay? Including the differential plus 1. But there is a differential plus 1, so what will be the increase in the port root? It should be an increase because this is 17, it is plus 1. So if we try to compute for the increment in the port root, dy now, we will use this one. Actually, you do not have to memorize this one. As long as you know differential calculus, you could derive it. Right? But I just closed this in the orange thing so you could put it in your mind, or you could forget it. As long as you know the so-called differential of an what you call this power function. Okay, you could derive this one. So if we now try to compute for dy will be equal to dx is 1, h plus 1. Because supposed to be the port root of 17 is greater than the port root of 16. So dy now will be equal to plus 1 over 4. Okay. Our x is actually 16. And 16 is actually it got a perfect fourth root. And 16 can be written as 2 to the fourth power. 2 times 2 times 2 is actually 16. But it can be written as 2 to the fourth. Raise that again to the 3/4 power. So this 4 here cancel with this. Right? So what remains will be 1 over 4. Okay? The remaining exponent will be 3. So this will be 2 to the third power. 2 to the third power is 8. So this is 8. So it will now be 1 over 32nd. If you divide 1 over 32nd, that is 0.3125. Meaning, the fourth root of 17 is actually 2 plus this increment here. Okay? And the increment that they were showing was actually this one, but it was actually derived from differential calculus. Right? So the fourth root of 17 now will be equal to 2, because 2 to the fourth is 16, plus the increment and the fourth root, which was computed by using differential calculus, it is 0.03125. So the total final answer now will be 2.03125. Okay? So we could check this one. 2.03125. Okay? We raise that to the fourth power. Y to the x. 4 equals. The remaining, the answer is actually 17.02, or this is almost 17. Okay? So this is correct. Okay? That's the way how to get a fourth root. You derive first the formula on how to take the increment by using differential calculus, or you could memorize this. Right? But as long as you know differential calculus, you could derive this one. So when you are getting a fourth root and it is not exact, to get the increment whether plus or minus, use this formula here. Okay, let's proceed with the square root. For the square root, the increment in the square root will be dx all over 2 the square root of x. Okay? For cube root, the increment in the cube root, if it is not exact, dx will be equal to, dy will be equal to dx over 3 times x raised to the 2/3. Actually, this was derived from differential calculus also. And so it is. Because if y here is actually equal to x raised to the 1/2, taking the differential will be 1/2. X raised to 1/2 minus 1 will be negative 1/2 times dx. So the increment in the square root will be equal to, we avoid the negative square root, negative power, right? So we bring down this one. So what remains will be dx over 2. X to the 1/2 is actually the square root. So this is actually the formula on how to get the increment of the square root of a number if it is not exact. Okay? That is dy is equal to dx over 2 the square root of x. For cube root, it is the same. dy is actually equal to dx over 3 x raised to the 2/3. It was derived from differential calculus. Y will be x raised to the 1/3, right? We are taking the cube root. dy will be equal to 1/3 times x raised to 1/3 minus 1 is actually minus 2/3 times dx. And dy is equal to, we place this negative exponent down, so what remains on the numerator will be dx all over 3 x raised to, this will now be raised to the 2/3. So this is the formula on how to take the increment in the cube root if the number is not a perfect cube. That is dy is equal to dx over 3 x raised to the 2/3. You don't have to memorize this. Okay? As long as you know differential calculus, you could derive it. But if you could memorize it, so be it. Good evening from Los Angeles.